This lesson is going to be focused on chemical equations and balancing equations. So you need to know how to write word equations, which means obviously using words. On the left-hand side, you have your reactants. Then you have an arrow, which in chemistry means equals. Then on the right-hand side, you have your products. So in this example, we have magnesium plus hydrochloric acid as the reactants, and magnesium chloride and hydrogen as the products. Now, if they say they want a chemical equation, then you have to use the proper symbols. So magnesium is a metal, so it exists on its own as Mg. Hydrochloric acid is HCl. Magnesium chloride, you will look at when you do ionic formulae. So it's MgCl2. And hydrogen is a gas and is diatomic, so it's H2. There's a 2 here in order to balance it. I will go over how to balancing later. But this is called a chemical equation. Always read the question carefully. If they do ask for state symbols, you must remember to put them in. So there are 4 state symbols possible. Little s means solid, little l means liquid, little g is gas, and AQ means aqueous, which means dissolved in water. There will be clues in the question as to what state symbol something is. All acids are always AQ, and water is always L unless it has been heated into a vapor. Then it'll be a gas. These are some general rules. And for most elements, the formula is the same as the symbol, but the main exceptions are the gases. So in your periodic table, if we have a look at any periodic table, here, we have the gases. So this one, this one, this one, this one, this one, this one. These are going to be diatomic. So 1, 2, 3, 4, 5, 6, even this one, okay, group 7. They exist as O2, N2, F2, and so on. And you can see this here. For compounds, they need to be learned either by heart, like ammonia is NH3, or the acids need to be learned by heart. And the organic compounds, when we do organic chemistry, need to be learned. For ionic compounds, you can use the crossover method that I show you in the ionic formulae topic. Now, balancing equations means you're allowed to put big numbers in front to multiply all the elements. You're not allowed to put little numbers, and I will show you what that means now. So if we look at balancing equations, equation sheet 1, so this one here, I will go over a few of these as an example. So let's start here. Now, unfortunately, I can't give you an exact method that's going to always work, because ultimately you need to have the same number of atoms on both sides. And that's because of the conservation of mass principle, where the total mass of the reactants equals the total mass of the products. So what you do is you look for where the atoms are not balanced. So here we have 1 calcium, 2 oxygens, 1 oxygen. Now, you're not allowed to put little 2 here. You're not allowed to put little subscript numbers. You have to put a big 2 in front. Now, that will mean that everything to the right of it is doubled. So not only is the oxygen doubled, but the calcium. So you have to put a 2 here to multiply the calcium. I'll show you one other little disclaimer. So say you had H2SO4. We have 4 oxygens, 1 sulfur, and 2 hydrogens. If we put a 3 in front, we now have 6 hydrogens. The sulfurs will be 3 because it's 3 times 1. And the oxygens will actually be 12. It's 3 times 4. I will give you one more example. ZnNO3 twice. Now, if I triple this, how many atoms do I have? Well, this subscript 2 applies to everything inside the bracket to the left of it. It does not apply to the zinc. So the zinc is only 1. So if you have a 3 in front, there will be 3 zincs. Now the nitrogens will be 2 times 1, which is 2, times 3, 6. The oxygens are 3 here, but there's a 2 here. So that makes 6 oxygens. then times 3 would make 18. So that's like the more complex version of counting atoms. With that aside, let's look at the second example. There's 2 sodiums and 1 sodium, so I'm going to put a 2 here. Now, there's 2 oxygens here and 2 hydrogens. I see 2 hydrogens here, and I see 1 plus 1, 2 oxygens. So it is now balanced. I recommend using a pencil when doing these. That might be the easiest way, because sometimes it's trial and error. Next one, aluminium. There's 2 here, so I'm going to put a 2 here. There's 3 oxygens, but 2 here. So what do? Don't be afraid to use a 0.5, so it'll be 1.5, because 1.5 times 2 is 3. The exam questions will always accept multiples. This is perfectly acceptable. Now, if you don't like it, you could double everything. So this will turn into 4. This will turn into 3. And this will turn into 2, which makes 6 oxygens, 4 aluminiums, 4 aluminiums. Okay, next one, we have 1 sodium and 2 chlorines, but only 1 chlorine here. So I'm going to put a 2 to make 2 chlorines, but you now have 2 sodiums, so I'm going to put a 2 here. And that is the general way of balancing the equations. They can obviously be harder. Now, while there was no set method here, I was looking at balancing the atoms. Questions such as 7, which are hydrocarbons, compounds made of hydrogen and carbon only. And when they're being burnt in oxygen to make carbon dioxide and water, there is a method you can actually use. I call it the Cho method. Always balance the carbon first, hydrogen second, and oxygen last. So there's 4 carbons here, so I'm going to put a 4 here. There are 8 hydrogens here, but only 2 here. So I'm going to put a 4, because 4 times 2 is 8. So I've done the carbons and hydrogens. Now the oxygens, there's 2 here, but here there's much more. So 4 times 2 is 8. Importantly, 4 times 1 is 4. 8 plus 4 is 12. What times 2 makes 12? Well, it's 6. So then the oxygen is done. So if you get one of these, you can lucky to balance it using the Cho method. So number 10 is similar as well. If I write out Cho, carbons first, 5 here, 5 here. Hydrogens are 12, 2 here, so 6 times 2 is 12. And oxygens, 5 times 2 is 10, and 6 times 1 is 6. So 10 plus 6 is 16. So this must be 8, because 8 times 2 is 16. And that's what we mean by putting big numbers in front. If you look at number 5, there's 2 sodiums, 1 carbon, 1 carbon, 3 oxygens, 1 plus 2 is 3, so it's already balanced. And lastly, number 6, there's 2 Ks, 1 K, so I'm going to put a 2. Now there's only 1 oxygen, unfortunately, but there's 2 here, so I'm going to multiply it by a half. As I told you, 0.5s are perfectly acceptable. Of course, you can double everything and you could get 4, 1, and 2 instead. But I prefer the 0.5s. Now, this topic requires a lot of practice. So my recommendation is that you practice on the worksheets attached in order to build up your speed and accuracy. Finally, I just want to mention what reversible reactions are. So reversible reactions are one that can go forwards and backwards, and they're shown by this symbol here. So forward and then backward. The particular reversible reactions that you need to know are the copper sulfate one and the ammonium chloride one. So you will see this again in the equilibria topic, but for now, it's just for you to be aware of the reversible arrow. So blue copper sulfate is hydrated. It looks like this. When you heat it, it turns to a white powder, and that's anhydrous copper sulfate, and water is given off. So that's the word equation, and this is now the chemical equation. Now you'll see this weird looking dot. It does not mean multiply. It means officially water of crystallization, which actually means that there's 5 water molecules inside every crystal. So there's a number of water molecules inside the crystal. You'll notice the state symbols are solid and solid because the white solid turns to a white solid. Now, you can reverse the reaction because if you take your white solid and you add some water to it, it turns blue. And that's because this plus this makes this. And that illustrates a reversible reaction. You lose the water at the beginning and you turn white. When you add the water back in, you turn blue. It is an endothermic process, but you will discuss more of this with me when we do the equilibrium topic. Lastly, let's have a look at ammonium chloride. This is the last part. So ammonium chloride, when heated, turns into ammonia and hydrogen chloride. Not hydrochloric acid because there's no water. It's just called hydrogen chloride, a toxic gas. Ammonium chloride is a white powder. Ammonia is an unpleasant smelling colorless gas. And HCl is kind of a white fume. So when you heat these in a test tube, actually the picture does show it nicely. You heat the white ammonium chloride, the white fume of HCl and the colorless NH3 will be released. And as it cools down near the top of the tube, these two are going to combine again to form the white solid ammonium chloride. So you've technically started with ammonium chloride here, you've heated it, it's turned into a gas which rises, 2 gases which rise, cool down, combine again, this one plus this one, and reform the ammonium chloride at the top. So these are reversible reactions that you can see with your eyes. That brings an end to the introduction to the formulae topic and balancing equations, which is actually just the first part here. And next, we're going to move into all the calculations with moles. So join me next time.